Let's move on from discrete random variables to continuous random variables. So we've talked a little bit about continuous random variables a little ways back, but now this is where we're going to focus on them. This is the first time when we're looking at random variables, that they can take on values in some interval of numbers. So it's not countably finite. You may be like, well, what do you mean? Let's take a look at some examples. Please pause the video and read example 9.1. So 9.1 is talking about heights and weights of American adults who participated in this survey. Now, what are the observational units? This is kind of a bit of a review too, just to keep the terminology fresh for us. Observational unit is each what? And hopefully you think, well, it's each American adult because that's who we're recording information on. The variables, what's varying, are height and weight. We see that here. Once again, I'm not going to write things down as a reminder. This is also to help you practice. So please, even if I don't write something down, do write something down. Variables are height and weight. We see those going to vary. Are they categorical or quantitative? Well, they're quantitative. We measure a value. Discrete or not? Now, I may be tempted to say, well, it's discrete. You weigh 171, let's say, in this case, it's kilograms, and you know what you weigh. But that's on let's say, a basic scale. Now you get a better scale, and you can go to tenths. Now you weigh 171.4 kilograms. Okay. Can you get more precise? Yes, you could get a better scale, and you could weigh 171 point, let's say, 432 kilograms, and you could keep going on and on. So are these measures essentially on a continuous scale? Yes. Could we reasonably model the probability distribution of these variables with a smooth curve? Well, let's see if it would make sense. Let's see if we do this. It's not going to be exact, but that would pretty well represent what's going on under that curve. Yeah, our curve, that looks pretty good to me. Let's see. And obviously you could fit this with software, which we're not going to do, but there we go. Smooth curves, sure, they would definitely pretty well represent, because remember the probability, what's happening, the probability, let's say that you weigh under 153 kilograms, is all of this here, okay? So that smooth curve would really well represent what's going on. Now, continuous random variable, they take on any value in some interval. There's an infinite number of possibilities. They're uncountable. So we can assume any value within a specified range. Remember that discrete random variables, all the values are listed, they're countable. We can actually enumerate, in other words, write them all out. Usually a continuous random variable is the result of a measurement, not always, but frequently it is. Every random variable has a probability distribution. When the random variable is continuous, the probability distribution is a smooth curve, because remember, there's an infinite number of possibilities. And here are some examples. The blue line here showing one possible, the red, another possible, and then this greenish yellowish color here, is depending on your screen. That may look familiar, and we'll be talking a lot more about that. That kind of looks like that normal distribution that hopefully you've seen before, but we'll be talking a lot about that very soon. Now, important characteristics of continuous probability distribution, the areas under the probability distribution correspond to probabilities. So if we want to know the probability between 0 and 2, let's say on the blue up here, the area would be between 0 and 2. This area here would be the probability of being between exactly 0 and 2. Now you can determine that area using calculus, that would be integrals, or other numerical methods, usually geometry, which would be finding the area with, let's say, of a rectangle. Now the total area under the curve is 1, because remember, this is a probability distribution. So to be a valid probability distribution, the sum of all the probabilities has to be 1. Now, if we want the probability at exactly a point, it is 0. And you may be like, well, why? Couldn't we just say exactly what that value is there? Remember, it's the area under the curve. What's the area of a line? And hopefully remember, oh, the area of a line is 0. We can't find it, an area of a line, because it has 0 width. Some examples of continuous random variables, remember, they can take on an infinite number of possibilities. Gas mileage of a randomly selected car. What are the possible values? Let's say that you have 30, you think it's 30 miles per gallon. That's what your little on your car it says when you look at the average miles per gallon. And then you have something that could actually test it more with more precision. You could have 30 point, let's say 2, 5, 4, 6, 7 miles per gallon. Okay, so many, many possibilities. Same thing with time. You could have a better and better and better time measurement device. Distance, once again, we talked about that earlier, and height. So how is a continuous probability distribution different and the same as a discrete probability distribution? Well, they both have to total. Here's where they're the same. The sum of the probabilities has to be 1 in either one of these distributions. Where they're very different is this, hopefully you can tell right away, is the continuous, and this is the discrete example. The discrete, it's very choppy. This is very smooth. Now we're going to look at a specific type of commonly used continuous distribution, the uniform distribution. And we'll do that in the next video.